September 5th, 1977. The world was different in ways that are hard to convey, not because the differences are subtle, but because they are total. The Soviet Union existed. The Berlin Wall existed. The personal computer did not exist. The internet did not exist. The mobile phone did not exist. GPS did not exist. The human genome had not been sequenced. HIV had not been identified. The hole in the ozone layer had not been discovered. Pluto was a planet. Scientists did not know that the universe's expansion was accelerating. No exoplanet had been confirmed. Most of the things that currently organize daily life on Earth, from the way we communicate to the way we navigate to the way we understand the origin of the universe, did not exist. On that day, from Cape Canaveral, Florida, a Titan III rocket lifted a spacecraft the size of a compact car from the surface of Earth and aimed it at Jupiter. The spacecraft was called Voyager 1. It is still flying. In 47 years, Voyager 1 has covered more distance than any human-made object in history. It is currently approximately 24 billion kilometers from Earth, roughly 163 times the Earth-Sun distance, in the space between the stars. It crossed the heliopause, the boundary of the solar system, on August 25, 2012, and became the first human-made object to enter interstellar space. It is still transmitting data. The signal takes approximately 22 hours and 30 minutes to reach Earth at the speed of light. Everything it left behind is the subject of this mission briefing. Not just the solar system, though the solar system is part of it. Not just the planets it visited, though they are part of it. Everything it left behind as it travelled. The science it deposited, the questions it opened, the people who built it, the civilization that launched it, the photograph it took of the world it was leaving, the boundary it crossed that no machine had crossed before. The full inventory of what Voyager 1 has left in its wake over 47 years of continuous flight. There is a specific quality to the Voyager 1 story that is different from the Voyager 2 story, which traces a clean geographic arc through 4 planetary systems to interstellar space. Voyager 1's story is not primarily geographic. It is temporal. It is the story of what a civilization becomes over 47 years relative to the artifact it launched, of the growing distance between the world that built the machine and the machine itself, of what it means to have sent something out in 1977 that is still sending back data in 2024. And it is the story of the specific things left behind at each stage of the journey, not as remnants or losses, as deposits, as the permanent additions to the human record that only happen when a machine flies somewhere and looks at things no machine has looked at before. If this is the kind of mission briefing you want more of, subscribe and stay with the crew. Strap in, we begin at the beginning, which is not September 1977. It is the world that made September 1977 possible, and what that world believed about itself when it built a machine and sent it to the stars. The specific world that built Voyager 1 is worth reconstructing carefully, because the reconstruction reveals something about the artifact that the artifact alone does not convey. The mid-1970s were the peak of NASA's post-Apollo confidence, or perhaps more accurately, the last days of it. The Apollo program had ended in 1972 with Apollo 17, the last crewed lunar mission. The agency that had put 12 people on the moon in 4 years was searching for its next act, navigating budget pressures and political questions about what human and robotic space exploration were actually for. The Viking missions to Mars, launched in 1975, were confirming that Mars's surface chemistry did not obviously support life. The Pioneer probes were already en route to Jupiter and beyond, returning the first close-range images of the gas giants. Into this context came the Voyager program, built on Gary Flandro's recognition of the 175-year planetary alignment window, and designed to exploit it before it closed. The program was funded, the spacecraft were built, the teams were assembled. The teams were young. Many of the scientists and engineers who designed the Voyager instruments and flight systems were in their 20s and 30s in the mid-1970s. They were the generation that had watched the Apollo landings as teenagers, that had been formed by the specific cultural moment of the space age, that believed in a quite direct way that humanity was on the way out into the solar system and that their careers would be spent executing that expansion. Some of those people are still alive, many are not. The specific cognitive experience, the combination of expertise and enthusiasm and cultural context that made the Voyager program what it was, exists now primarily in the artifacts the program produced, the spacecraft, the data, the scientific papers, the oral histories, the photographs of the teams at their consoles during the planetary encounters. Voyager 1's computers had less processing power than a modern thermostat. The data storage system used magnetic tape. The transmission rate from Saturn was approximately 44 kilobits per second, roughly equivalent to a very slow dial-up internet connection. The images were recorded on tape aboard the spacecraft and then played back to Earth at the highest bandwidth the transmission system could sustain. The engineers made these constraints work through extraordinary design discipline. Every bit of data mattered. Every minute of observation time was scheduled in advance and optimized. The science teams knew they would get exactly one pass at each planet, and they designed their observation sequences to extract the maximum scientific value from the hours of closest approach. What they did not fully know, could not have fully known from the available prior observations, was what they would actually find. Every planetary encounter was an encounter with genuine uncertainty. The predictions were detailed and sophisticated, built on decades of telescopic observation and the limited close-range data from the Pioneer probes. They were also wrong in specific ways at each destination that made the actual findings more interesting than the predictions. This is the specific gift that Voyager 1 deposited at each encounter, the correction of the prior model, the update to human understanding that could only come from actually being there. The world of September 1977 deserves more specific reconstruction, because the gap between that world and the present is precisely what makes Voyager 1 extraordinary as an artifact. Jimmy Carter was the President of the United States. The Soviet Union, under Leonid Brezhnev, was in the middle of a period of relative stability that would end with the invasion of Afghanistan in 1979. The Cold War was the dominant fact of international relations. The strategic rivalry between the two superpowers organized most of global politics and military planning in a way that is difficult to explain to anyone who did not experience it. Star Wars had been released in theaters 4 months earlier. It was still showing. Its depiction of space travel as fast and casual and full of alien worlds was roughly as accurate to real space exploration as a Western movie is to the actual experience of cattle ranching, which is to say, not very, but it was shaping the popular imagination of space in a way that the real space program could not match for drama. Saturday Night Fever had not yet been released. The Clash's first album had come out 6 months earlier. Elvis Presley had died 6 weeks earlier. The world was organized around information that traveled by newspaper and television and radio, and telephone and physical mail. Information did not travel at the speed of light across global networks. The internet existed in a limited form as ARPANET, connecting a handful of university research computers, and was not accessible to anyone outside that specific community. The computers used to design Voyager 1 were mainframes the size of rooms, operated by specialists using punch cards and magnetic tape. The microprocessors used to navigate the spacecraft were based on technology that would not be commercially available to the general public for another few years in the form of the first personal computers. Apple Computer had been incorporated 5 months earlier. Microsoft would not release its first retail product for 3 more years. A calculator that could compute the trigonometric functions needed for orbital mechanics cost several $100s and was a professional instrument, not a consumer product. Pocket calculators had existed for only a few years. Students doing physics calculations still sometimes use slide rules. The launch of Voyager 1 was significant news. It was covered by television and newspapers. The specific technical achievements involved, the trajectory calculations, the instrument designs, the communication system, were accessible enough to a technically educated audience that the coverage could explain some of what was being done and why. NASA was still a civilian space agency that attracted significant public attention, operating in the cultural context shaped by the Apollo missions a decade earlier. The people who gathered to watch the launch at Cape Canaveral, the engineers and scientists and dignitaries and press, were watching a rocket carry 47 years of future away from the planet. None of them knew it would still be transmitting in 2024. The planned mission duration was 4 years through the Jupiter and Saturn encounters. The extended mission, the long crossing to the heliopause and beyond, was not on any planning document in 1977. The world they inhabited, with its Cold War and its analog technology, and its pre-internet communications and its specific mix of anxiety and optimism about what the future would bring, is as remote from 2024 as 1930 was from 1977. Not because 47 years is an extraordinarily long time by historical standards, because the specific technologies that organize daily human life have changed so completely that the practical experience of being alive is categorically different. Voyager 1 came from that world. It carries that world in every component and every design decision and every line of code in its onboard computers. It is an artifact from a civilization that, in the most important practical senses, no longer exists. The civilization of 2024 inherited it but did not build it. The people who will receive the last signal from Voyager 1 in the 2030s will be working to communicate with a machine designed by people, most of whom they never met, built with tools they have never used, launched from a world they know only as history. This is the specific character of Voyager 1 as a human artifact. It is not just a spacecraft. It is a message from one civilization to a later one, a message that the later civilization can receive because the machine still functions, that it can interpret because the physics is the same, and that it can be moved by because the human questions the mission asked are questions the later civilization is still asking. That the message still arrives is itself the deposit. The first deposit came at Jupiter in March 1979, and it came from a moon that was not the focus of the encounter. On March 8th, 1979, 3 days after Voyager 1's closest approach to Jupiter, a navigation engineer named Linda Morabito was examining images of Jupiter's moon Io. She was not looking at Io for scientific purposes. She was using the images for navigation, specifically to verify the spacecraft's position by measuring the position of Io against the background of stars. It was routine work, the kind of careful positional measurement that navigation engineers did regularly to keep track of where Voyager 1 actually was in space. And then she saw the plume. On one of the images, extending above the limb of Io on the side facing away from Jupiter, there was a crescent-shaped structure that did not belong. It was too large to be an artifact of the imaging system. It was too regular to be a shadow. It extended hundreds of kilometers above the surface of the moon, curving away into space in the distinctive shape of a volcanic eruption column seen from the side. Morabito looked at it for a while. Then she told her supervisor. The Voyager science team examined the image. They considered and rejected various non-volcanic explanations. They looked at other images of Io from the encounter, images that had been taken for entirely different purposes, but that happened to contain Io in the background. Some of those images showed the same structure. Some showed it from different angles, some showed other different plumes at different locations on Io. Io was erupting, not one volcano, multiple volcanoes erupting simultaneously, with plumes rising to heights that dwarfed any volcanic eruption in Earth's recorded history. The largest plume observed, later named Pele, rose approximately 300 kilometers above the surface and was depositing material in a ring roughly 1,200 kilometers in diameter. Before this moment, active volcanism had been observed on one body in the solar system, Earth. The other known volcanic features in the solar system, on Mars, on Venus, as inferred from various evidence, on the Moon in its ancient past, were all either dormant or extinct. The assumption that volcanism required a sufficiently large body to retain internal heat had not been formally stated as a law, but it was implicit in every model of small-body geology. Io is only slightly larger than Earth's moon. Its radius is 1,821 kilometers. Under the prior model, it should have been cold and dead. It was not. Voyager 1 left behind at Jupiter the discovery that the universe had been operating on a different rule than anyone had known. The discovery that small bodies could be geologically active through a mechanism that had nothing to do with their size or their age. Tidal heating, the flexing of the interior by the gravity of a nearby giant. Io's internal heat came from Jupiter. It was maintained by the orbital dynamics of the Jovian moon system. It was a form of geological activity that the Earth-centric model of volcanology had not anticipated. The science deposited by this single discovery is extensive and still being added to. Every subsequent visit to Io by the Galileo and Juno orbiters has built on the foundation Voyager 1 left behind. The theory of tidal heating that was developed to explain Io became the framework for understanding Europa's subsurface ocean, Enceladus's geysers, and potentially a large fraction of the habitable environments in the outer solar system and in planetary systems around other stars. If tidal heating can maintain a liquid water ocean under the ice of Europa, then similar conditions might exist around giant planets in other stellar systems, at distances from their stars where solar heating alone would be insufficient. The habitable zone, the traditional conception of the region around a star warm enough for liquid water, was expanded by the discovery on Io to include tidal heating as a co-equal source of the energy needed for habitability. This is the kind of deposit Voyager 1 left behind. Not just a data point, a reframing, a new understanding of what is possible, grounded in direct observation of a world that had been theorized about for centuries and seen up close for the first time in 1979. Jupiter also left something for Voyager 1, the speed it needed to continue. The Jupiter gravity assist added velocity to Voyager 1's trajectory and redirected it towards Saturn. The specific trajectory chosen for Voyager 1, unlike Voyager 2's, which was designed for the full Grand Tour, was optimized for a close encounter with Titan, Saturn's large atmospheric moon, at the cost of a trajectory that would swing Voyager 1 above the ecliptic plane and end its planetary encounter sequence at Saturn. This was a deliberate choice. The science team believed, correctly as it turned out, that Titan represented a uniquely important target. A moon with a thick atmosphere was extraordinarily rare in the solar system. Understanding that atmosphere required the closest possible approach, the Grand Tour trajectory that Voyager 2 would follow was not compatible with a close Titan encounter. Voyager 1 was given Titan. The Jupiter encounter left behind science that continues to be extracted from it more than 45 years later. The specific properties of Jupiter's magnetosphere that Voyager 1 measured in March 1979, the structure of the radiation belts, the dynamics of the interaction between the magnetosphere and Io's volcanic output, the detailed topology of the magnetic field lines threading through the system, are still the subject of active research. The Juno mission, in orbit around Jupiter since 2016, has provided much more detailed measurements of Jupiter's interior structure and magnetic field, but the temporal baseline of the Voyager observations, made decades before Juno, is scientifically valuable because it allows researchers to study how the system has changed over time. The plasma physics of the Jovian magnetosphere is one of the best studied natural laboratory environments for magnetohydrodynamics, the physics of electrically conducting fluids in magnetic fields. The extreme conditions near Jupiter, the combination of the strongest magnetic field of any planet except possibly Saturn, the intense radiation belts, the continuous injection of sulfur and oxygen ions from Io's volcanism, and the rapid rotation of the entire system with a period of about 10 hours create dynamics that do not exist anywhere near Earth and that cannot be studied in terrestrial laboratories. The Galilean moon system, whose dynamics Voyager 1 characterized in its first close-up look, has become one of the central fields of outer solar system research. The four large moons, Io, Europa, Ganymede, and Callisto, represent four different points on the spectrum of geological activity driven by tidal heating, and studying them together provides insights into the relationship between tidal dissipation and geological activity that applies to planetary systems around other stars. The specific discovery of Io's volcanic activity has been extended in ways that would have been astonishing to the Voyager team in 1979. The Galileo mission found that the heat flow from Io's surface was much higher than even the Voyager observation suggested. Juno has made close flybys of Io, obtaining the best yet images of its volcanic surface and measuring the thermal emission of individual volcanoes. The global heat flow from Io, totaling roughly 2 watts per square meter averaged over the surface, is more than 30 times Earth's global heat flow, despite Io being a smaller body. The implications for exoplanet astrobiology that have been derived from the Io discovery are more diffuse but potentially more important. If tidal heating can maintain geological activity on a small moon, and if that geological activity can drive ocean floor hydrothermal chemistry, as it does at Earth's mid-ocean ridges, then the habitable environments in any planetary system are not limited to the narrow zone where stellar radiation alone provides sufficient heat for liquid water. They extend to any moon or planet that orbits close enough to a massive body to experience significant tidal dissipation. The galaxy's habitable volume, if tidal heating is included as a potential energy source, is substantially larger than the galaxy's habitable volume if only stellar radiation is considered. This is not a trivial restatement. It is a change in how we estimate the likelihood of life existing elsewhere in the cosmos. Voyager 1 left that change behind at Jupiter in March 1979. It was not the only spacecraft to see Io's volcanism. Voyager 2 confirmed the discovery 4 months later. But Voyager 1 was first. Linda Morabito was first. The navigation engineer doing routine work who stopped and looked at the image and said something is wrong here, and kept looking until she understood what the something was. The history of scientific discovery has this character repeatedly. The discovery that changes a framework often comes from someone doing routine work who notices an anomaly and is curious enough to pursue it rather than file it away as a measurement artifact. Voyager 1 left behind not just the specific discovery, it left behind that example, the example of what scientific observation actually looks like, which is not always a researcher aiming a dedicated instrument at a suspected phenomenon. It is sometimes a navigator checking a position fix who cannot explain a crescent above a moon's limb. And Titan gave Voyager 1 one of the most frustrating and ultimately most consequential observations of the entire Voyager program. Titan is the second largest moon in the solar system, smaller than Ganymede but larger than Mercury. It orbits Saturn at a distance of roughly 1.2 million kilometers, completing one orbit every 16 days. It is the only moon in the solar system with a dense atmosphere, and its atmosphere is the only primarily nitrogen atmosphere in the solar system other than Earth's. That last fact is significant, not because nitrogen atmospheres are themselves remarkable, but because nitrogen is a prerequisite for the specific kind of chemistry that produces amino acids and the building blocks of life as we know it. A dense nitrogen atmosphere with other trace gases creates the conditions for complex organic chemistry. From Earth, Titan was observable, but not characterizable in any useful detail. It was a disk too small to resolve surface features. The atmosphere was known to contain methane, detected spectroscopically, and the presence of a thick atmospheric haze was inferred from the way Titan's brightness varied. But what was beneath the haze, what the surface was like, whether liquid methane or ethane might pool on the surface in the way water pools on Earth, was genuinely unknown. Voyager 1 passed within approximately 4,000 kilometers of Titan's surface on November 12, 1980. The cameras revealed nothing visible, that is. The thick atmospheric haze that had been inferred from Earth-based observations proved to be completely opaque in visible light. Where the science team had hoped to see the surface, perhaps with mountains or seas or geological features, they saw only the uniform orange-brown of the haze layer. The surface of Titan was hidden behind a curtain that Voyager 1's cameras could not penetrate. This was not a failure. It was a discovery. The haze was itself scientifically important. The specific properties of the haze, the particle sizes, the chemical composition, the altitude distribution, told the science team things about Titan's atmospheric chemistry that Earth-based observation could not have revealed. The haze was composed of complex organic molecules, the product of solar ultraviolet radiation acting on methane and nitrogen in the upper atmosphere. Titan's atmosphere was not just chemically complex, it was processing sunlight into organic molecules and depositing them as haze throughout the atmosphere. But the science team wanted the surface. They had aimed their best instrument, the spacecraft's closest approach, at a moon and been given a wall of fog, and then the radio occultation data came back. As Voyager 1 passed behind Titan, its radio signal to Earth was refracted through Titan's atmosphere. By carefully measuring how the signal was bent and attenuated, the science team could measure the atmospheric temperature and pressure profile at each altitude through which the signal passed. The data showed an atmosphere nearly 1.5 times as dense as Earth's at the surface, with a surface temperature of approximately -179 degrees Celsius. That temperature, combined with the atmospheric composition and pressure, placed Titan in the specific range where methane can exist in all three phases: solid, liquid, and gas. On Earth, water does this. Rain falls, pools in lakes and rivers, evaporates, forms clouds, rains again. On Titan, methane does the same thing. The Voyager data was the first direct evidence that another world in the solar system might have active meteorology, a cycling of a substance through phase changes that drives weather and modifies the surface. The surface temperature of -179 degrees Celsius makes liquid water impossible, but it makes liquid methane and ethane possible, and the organic molecules being produced in Titan's atmosphere and raining onto the surface are complex enough that some researchers have speculated about a form of chemistry that could produce metabolic processes in liquid methane, a life based on fundamentally different chemistry from Earth's. This is extremely speculative, but the speculation exists because of what Voyager 1 left behind at Titan. Voyager 1 left behind the discovery that Titan has conditions that no simple model of the outer solar system had predicted. An active methane cycle, a dense organic-laden atmosphere, and a surface hidden beneath haze but almost certainly interesting in ways the data strongly implied. It left behind a mystery that would not be resolved until the Cassini-Huygens mission arrived at Saturn in 2004, and the Huygens probe descended through Titan's atmosphere in January 2005, returning images of a surface covered in rounded pebbles of water ice polished by methane rain, with rivers and tributaries cut by the same methane flow and emptying into what appeared to be a dry lac bed. What Huygens confirmed in 2005 was essentially what Voyager 1 implied in 1980. The difference was 25 years and the ability to actually get below the haze. Voyager 1 left that implication behind. It left behind the question in such compelling form that the planetary science community spent the next 2 decades building the mission needed to answer it. The frustration of Titan's opacity, which prevented Voyager 1 from seeing the surface it had come so far to examine, is worth examining as a scientific episode rather than simply as a limitation. The decision to aim Voyager 1 at Titan was made with full knowledge that the atmosphere might be opaque. Earth-based spectroscopy had detected atmospheric methane and the reddish haze that methane photolysis products produce. The science team knew there was a real risk that the cameras would show nothing but orange fog. They went anyway. This is the specific character of the First Look mission. You do not know what you will find. You know you will find something. You know that the something you find will be more interesting than the predictions, because the predictions are always based on incomplete information, and the universe reliably exceeds its models. Titan exceeded its models in the specific direction that was expected. The atmosphere was there, it was thick, it was opaque, but it exceeded them in the depth of the atmospheric chemistry as well. The specific organic molecules identified in the haze, the phthalates and nitriles and complex hydrocarbons, were more abundant and more diverse than the simplest photochemical models had predicted. The atmosphere of Titan was a more active chemical reactor than anyone had modelled. The concept of Titan as a slow-motion Earth analogue, a world where the same broad categories of chemistry play out in a different medium at a different temperature, was a product of the Voyager 1 encounter. The thick nitrogen atmosphere, the methane cycle analogous to Earth's water cycle, the complex organic chemistry raining onto the surface and pooling in lakes and rivers, the possibility of a chemistry that might produce something analogous to a prebiotic soup in liquid methane. All of these ideas were stimulated by the data Voyager 1 left behind at Titan in November 1980. The Cassini-Huygens mission that eventually characterized Titan in detail was one of the most ambitious and expensive planetary missions ever undertaken, developed by NASA and ESA jointly at a cost of roughly $3 billion and taking approximately 20 years from conception to the first Saturn orbit in 2004. The scientific case for the mission rested almost entirely on the foundation that Voyager 1 established. Without the Voyager 1 data, the case for spending that kind of resource on a dedicated Titan mission would have been harder to make. The Huygens probe, which descended through Titan's atmosphere on January 14, 2005, sending back images for about 72 minutes on the surface before its batteries failed, showed exactly the kind of environment that Voyager 1's data implied. A landscape shaped by methane rain, with river channels cut by the same erosive process that cuts rivers on Earth, but in a different fluid, rounded pebbles of water ice, polished by liquid methane flow, and a bright highland region adjacent to a darker lowland that might be a dried methane lake. The specific image of pebbles of water ice, looking almost exactly like the river pebbles you can pick up from any terrestrial streambed, was one of the most emotionally resonant images in the history of planetary exploration. Not because it showed something dramatically exotic, but because it showed something familiar in a completely alien context. Rounded pebbles, the shape that flowing liquid makes of solid material, regardless of what the liquid and the solid are, regardless of the temperature, regardless of the planet. Voyager 1 left behind the question that Huygens answered with that image of pebbles. The question, what does a world with an active hydrological cycle look like when the liquid is methane and the temperature is minus 179 degrees Celsius? The answer, it looks like a river valley. It looks like something you have seen before, because the physics of erosion is the same. The materials are different, the temperature is different, the physics is the same. That is one of the most profound things that Voyager 1 left behind, evidence that the same physical processes that shape Earth operate elsewhere in the solar system, in forms that are alien in their specifics and familiar in their patterns. After Saturn and Titan, Voyager 1's trajectory carried it above the ecliptic plane, out of the plane in which the planets orbit. The grand tour was finished. Jupiter and Saturn were behind it. The planetary science phase of the mission was over. But the mission was not over. It had barely begun. What lay ahead was the long crossing, and what Voyager 1 would leave behind in the rest of the journey was different in kind from the planetary science. It was something more personal, more philosophical, more specifically about us. There is a specific reason that the pale blue dot photograph has the emotional power it does, and it is worth unpacking because the power is not accidental. Most photographs that are intended to produce awe do so by showing something large. The pillars of creation, the galaxy clusters in the Hubble ultra-deep field, the surface of the sun in X-ray wavelengths. These images work by putting enormous things in front of you and asking you to feel the scale. The pale blue dot works by putting a small thing in front of you, by making the large thing small, by showing you from the outside that the enormous and consequential world you live in is from any cosmic perspective a point. The cognitive operation the photograph requires is different from the cognitive operation of a large-scale astronomical image. Looking at the pillars of creation, you look out from Earth toward something vast. Looking at the pale blue dot, you look back at Earth from something vast. The direction of the gaze is reversed. The observer is no longer on the pale blue dot looking outward. The observer has been transported to a vantage point 6 billion kilometers away and is looking back. This reversal has a specific psychological effect. It produces what psychologists call the overview effect, a term coined for the experience astronauts report when they see Earth from space and describe a shift in their sense of the planet's fragility and preciousness. The pale blue dot produces a version of this effect for people who have never left Earth, by simulating the view from outside. Carl Sagan's essay amplifies the photographic effect by making explicit what the image implies. The essay is not interpreting the image for a naive audience. It is articulating the logical and emotional conclusions that follow from what the image shows. The rivers of blood spilled by conquerors and kings over a point in cosmic dust. Our planet a lonely speck in the great enveloping cosmic dark. There is no hint in the image that help will come from elsewhere to save us from ourselves. These conclusions are not pleasant. They are not the kind of conclusions that most public communication about space emphasizes. Space exploration typically emphasizes expansion, discovery, the adventure of going further. The pale blue dot inverts this. It emphasizes smallness, isolation, the impossibility of escape from the consequences of what we do to the world we have. The essay was published in 1994 in Sagan's book of the same name. It has been reproduced endlessly, set to music, read aloud by Sagan in recordings that circulate on the internet, quoted in commencement addresses and environmental speeches and arguments about the futility of war. It has become one of the most frequently cited texts in popular scientific writing, which is a remarkable achievement for a text that is essentially a meditation on human smallness. Voyager, one left behind the experience this essay describes. Not because the image required the essay to produce an effect, though the essay amplified the effect. Because the image, taken from a place no human had ever been, made visible something that was always true but had never been made visible before. That Earth is a point in space, unremarkable from any cosmic perspective, small and alone and dependent entirely on the good judgment of the beings who happen to inhabit it. This is a sobering truth that Voyager 1 deposited in the human record in February 1990. Not a new truth, but a seen truth, a photographed truth, a truth that can be pointed to and said, here is the evidence. That is a different kind of scientific deposit from the discovery of Io's volcanism or the characterization of Titan's atmosphere. It is a deposit of perspective rather than information. But perspective changes behavior in ways that information alone sometimes cannot. Whether the pale blue dot perspective has changed behavior in any measurable way is genuinely uncertain. The environmental and political crises that Sagan's essay names as symptoms of our failure to understand our situation have not been obviously resolved in the 30 years since the essay was published. But the image and the essay are part of the cultural context in which those crises are discussed. And cultural context shapes what ideas seem plausible and what goals seem worth pursuing. Voyager 1 deposited a perspective. How that perspective is used is our responsibility. On February 14th, 1990, At the instruction of Carl Sagan, Voyager 1 turned its camera backward. The spacecraft was approximately 6 billion kilometers from Earth, outside the orbit of Neptune, having completed its planetary encounters and been flying through the outer solar system for more than a decade. Sagan had proposed since at least 1981 that as Voyager 1 reached sufficient distance, it should look back and photograph the solar system, creating a mosaic of images showing the planets from the outside. The proposal was not universally popular at JPL. Pointing the camera back toward the sun risked damaging the camera's light-sensitive detector. The scientific value of the images was limited. No new science would be accomplished. The images would show only dim points of light, the planets as they appeared from interstellar distance. The proposal was eventually approved, and on Valentine's Day 1990, Voyager 1 took a series of 60 images, assembling a mosaic of the solar system from the outside. In one of those images, Earth appeared. It appeared as a pale blue point of light, occupying less than a single pixel of the camera's detector, suspended in a beam of scattered sunlight that crossed the image like a solar ray. The image was processed and examined. Carl Sagan looked at it, and then he wrote about what he saw. The passage he wrote has been read by millions of people, and is often described as the most important piece of scientific writing of the 20th century, which is a claim so large that it cannot be objectively verified, but that captures something true about the response the text produces. The passage describes Earth as a pale blue dot, a mote of dust suspended in a sunbeam. It describes the human history of violence and territorial conquest and religious certainty as taking place on a pale blue dot in the vast cosmic dark. It argues that the image underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. The image was not scientifically significant in the technical sense. No new information about Earth was contained in it. Earth looked, from 6 billion kilometers, exactly as physics predicted it would look. The pale blue color was the expected result of light scattering in the atmosphere. The tiny angular size was straightforward geometry. What the image was a perspective. A specific, measured, documented perspective on Earth from a distance that no human eye had ever occupied. The perspective that Copernicus had implied and Galileo had confirmed, and every space exploration mission had reinforced, the perspective that Earth is a small object in an enormous universe, was here made visceral in a way that abstract understanding does not produce. Before the pale blue dot, people knew Earth was small compared to the universe. After the pale blue dot, people felt it. There is a specific neurological difference between these two states. Knowing something as a propositional fact and experiencing it as a felt reality engage different parts of the brain and produce different behaviors. The pale blue dot photograph changed the felt reality of many people's relationship to Earth. Voyager 1 left this behind. Not just the image, though the image is the deposit, the perspective, the specific and irreproducible visual argument that you can only make from 6 billion kilometers away. The photograph has been reproduced billions of times. It hangs on walls and appears on book covers and is referenced in environmental arguments and cosmic humility arguments, and arguments about the preciousness of Earth as a habitable world. It is one of the most reproduced images in the history of photography, taking as photography the broader category that includes astrophotography and remote sensing and scientific imaging of worlds. What Voyager 1 left behind in February 1990 was a photograph. What that photograph left behind was a change in how we see ourselves. This is a harder thing to account for than a scientific discovery. Scientific discoveries can be cited and extended and confirmed and revised. The change in felt reality produced by an image is not easily measured. It is not a variable in a database. It is not a number that goes into a model, but it is real. And it is part of the legacy of Voyager 1 in a way that cannot be omitted from any honest accounting of what the mission left behind. There is one more dimension of the pale blue dot worth considering. It was Carl Sagan's idea. Sagan died in December 1996, 6 years after the photograph was taken. He is the person most associated with the pale blue dot's cultural significance, both because he conceived the observation and because he wrote the text that gave the image its particular emotional weight. Sagan is himself part of what Voyager 1 left behind. Not in the sense that Voyager 1 caused his death, obviously, but in the sense that the Voyager missions were a central part of Sagan's life and career, and that his engagement with them produced work. The pale blue dot essay, Cosmos, the argument for SETI, the golden record that has outlasted him. The person who best articulated what Voyager 1 meant for human self-understanding is gone. What he said remains. This is the pattern of everything Voyager 1 left behind. The people are gone. The things they made remain. The spacecraft recedes. The science accumulates. The photographs are reproduced. The culture changes in ways that are hard to trace to any single cause, but that have the Voyager missions woven through them. Voyager 1 left behind a changed relationship between humanity and its sense of place in the universe, and it left behind the image that made that change visible. The heliosphere crossing in 2012 is remarkable not just as a scientific milestone, but as an example of how science works across decades. The heliopause, the boundary Voyager 1 crossed, was predicted by theoretical work that began in the 1950s and 1960s. Eugene Parker's theoretical description of the solar wind in 1958, which was initially rejected by reviewers as implausible and published only after the editor overruled them, established the framework within which the heliosphere and its boundaries were eventually understood. Parker's solar wind model was confirmed by spacecraft observations within a few years, and the existence of a heliopause where the solar wind meets the interstellar medium became an accepted prediction of the model. Predicting the existence of the heliopause and knowing where it actually is and what it is actually like are different things. The specific location of the heliopause depends on the balance between the solar wind pressure, which varies with solar activity, and the interstellar medium pressure, which depends on the local density and magnetic field of the interstellar medium in the Sun's vicinity. None of these quantities was known with sufficient precision in the 1970s to predict the heliopause distance accurately. The models that existed when Voyager 1 launched predicted the heliopause at roughly 50 to 100 astronomical units. The actual crossing occurred at approximately 121 astronomical units. This is roughly consistent with the predicted range, but at the upper end, suggesting that either the solar wind pressure is higher than the median model assumed, or the interstellar medium pressure in this direction is lower. The asymmetry of the heliosphere, revealed by the fact that Voyager 1 and Voyager 2 crossed the heliopause at different distances from the Sun, in different directions, tells us something about the local interstellar environment. The heliosphere is not a perfect sphere. It is compressed on the side facing the direction of the solar system's motion through the galaxy, the upstream side, and extended into a tail on the downstream side. Voyager 1 crossed in the upstream region. Voyager 2 crossed in the flank region. The different crossing distances reflect the different pressures at these different locations. This kind of three-dimensional characterization of the heliosphere's shape was not possible from any vantage point inside the heliosphere. It required actually crossing the boundary. Voyager 1 and Voyager 2 provided the only two direct measurements of the heliopause crossing ever made, from the only two locations in the heliosphere from which the boundary had been crossed. The plasma science instrument on Voyager 1 had stopped working in 1980, 8 years before Voyager 2's was still operating. The loss of the plasma science instrument meant that Voyager 1's crossing could only be inferred from other instruments, primarily the magnetic field instrument and the cosmic ray instrument. The inference was robust, but it lacked the direct plasma density measurement that would have definitively confirmed the crossing. This is one of the frustrating aspects of the Voyager 1 heliosphere story. The most definitive instrument for measuring the crossing was not working. The crossing was inferred from consistent changes in multiple other instruments, and the inference has been accepted by the scientific community, but it required the careful assembly of evidence from multiple partial datasets, rather than a single definitive measurement. Science very often works this way. The clearest experiment is not available. The data you have is imperfect. You build the best case you can from what you have, and you acknowledge the limitations clearly, and the community evaluates whether the evidence is sufficient to support the conclusion. In the case of Voyager 1's heliopause crossing, the community concluded it was. Voyager 1 left behind the methodology as well as the data. The methodology of making inferences from imperfect, partial, indirect measurements in environments too hostile and remote for direct human access. This methodology is what planetary and heliospheric science actually consists of. It is not the clean, decisive experiment of a laboratory setting. It is the careful assembly of consistent evidence from multiple imperfect instruments over extended time periods. That methodology, practiced on Voyager 1 data for 47 years, has been applied by every subsequent mission. The deposit is invisible in the sense that it does not show up in any individual database, but it is real in the sense that the scientists who learned to do planetary science by analysing Voyager data took that methodological training into everything else they did. After the pale blue dot photographs in 1990, Voyager 1 continued outward into the outer solar system and the long crossing to the heliosphere. This phase of the mission is the least dramatic in terms of specific events, but the most dramatic in terms of what it means that the journey was made at all. For 22 years after the pale blue dot, from 1990 to 2012, Voyager 1 crossed the heliosphere. This is not a region that had been visited before. The heliosphere, the bubble of solar wind plasma that surrounds the solar system, had been theorized and partially characterized by Earth-based and near-Earth observations. Its outer boundary, the heliopause where the solar wind meets the interstellar medium, had been predicted but not directly observed. Nobody knew exactly how far it was, what conditions were like in the heliosheath between the termination shock and the heliopause, or what precisely was on the other side. Voyager 1 knew. Or rather, Voyager 1's instruments measured, and the measurements told us things we had not known. The termination shock, the inner boundary of the heliosheath where the solar wind slows from supersonic to subsonic as it encounters the pressure of the interstellar medium, was first detected by Voyager 1 in approximately 2004, at a distance of roughly 94 astronomical units from the Sun. The crossing was not sharp, as some models had predicted, but gradual, suggesting a more complex interaction between the solar wind and the interstellar medium than the simplest models described. The heliosheath itself, the turbulent region between the termination shock and the heliopause, occupied Voyager 1's instruments for approximately 8 years. This was an entirely new environment, unlike anything closer to the Sun, and the data returned from it constituted the first measurements of conditions in this specific region of space. The magnetic field was different, the particle energies were different, the dynamics were different, and then, on August 25, 2012, the plasma science experiment on Voyager 1 failed. This was not an anomaly. The instrument had been turned off years earlier to conserve power. But on August 25, 2012, the data from other instruments showed a sudden change that researchers eventually confirmed as the crossing of the heliopause. The evidence was specific. The density of particles from the solar wind dropped abruptly. The cosmic ray flux from the galaxy, which the solar wind had been modulating, increased sharply. The magnetic field direction, which inside the heliosphere is dominated by the Sun's field, shifted toward the direction of the local interstellar magnetic field. Voyager 1 was in interstellar space. Not at the edge of the solar system, if by solar system you mean the region under the Sun's gravitational dominance. The Oort cloud, which extends to roughly 100,000 astronomical units, is still gravitationally part of the solar system. Voyager 1 is nowhere near the Oort cloud, but it was outside the heliosphere, in the space between the stars, and it was the first human-made object ever to be there. The confirmation of the crossing required careful analysis and debate that lasted for months. The science paper announcing the crossing was published in September 2013, a year after the crossing itself, and still generated scientific discussion about the precise boundary conditions. Some researchers argued that Voyager 1 had not crossed the heliopause itself, but an intermediate magnetic boundary. The Voyager team and most of the scientific community concluded that the 2012 crossing was genuine. What Voyager 1 left behind at the heliopause was the first direct measurement of what that boundary is actually like, not what models predicted, what instruments actually measured from inside it as it was crossed. The interstellar medium that Voyager 1 entered turned out to be slightly different from the predictions. The temperature was higher than expected. The density of certain particle species was different from predictions. The magnetic field direction did not match all models of the local interstellar field. Each of these discrepancies is a deposit. Each one is a case where the actual measurement corrects the prior model. Each one is data that will be absorbed into the next generation of heliospheric models and will change, slightly or substantially, what those models predict about the interaction between the solar system and its galactic environment. This process of measurement, correction, refinement, and revised model is the specific way science works, and the specific way Voyager 1 has been contributing to it since 1977. Every unexpected finding is a gift to the science. Every model correction is what the mission leaves behind. Voyager 1 is still leaving deposits. It is still returning data. The data is from the interstellar medium, from a region that no other instrument has ever sampled, about conditions that are unique to this specific location and this specific time in the solar system's traversal of the local interstellar medium. The deposits are smaller now, because the remaining instruments are few and the data transmission bandwidth is limited. But they are real, and they will continue until the power finally fails. The power will fail, the signal will stop, the last deposit will be made, and then Voyager 1 will continue in silence, following the trajectory that physics assigned it in 1977 for a very long time. The golden record raises a specific question about communication across radical difference that is worth examining as a scientific problem rather than just a cultural or philosophical one. The problem of communicating with a hypothetical extraterrestrial intelligence that has no prior knowledge of human existence or human sensory systems or human culture is the most extreme version of a communication problem that humans face in scaled-down versions in cross-cultural communication, in communication across time through historical texts, and in communication between species in the form of animal behavior studies. The record's designers made specific choices about what is communicable across radical difference and what is not. Mathematics is communicable across radical difference, because mathematics describes relationships that hold, regardless of the physical substrate of the reasoning system. The hydrogen spin-flip frequency is a mathematical relationship between physical constants that any civilization capable of doing physics has encountered. The diagrams on the record's cover that use this frequency as a unit of measurement are communicable to any civilization with that physics. Scientific information about human biology, expressed in the images through anatomical diagrams and genetic diagrams, is potentially communicable in the sense that a sufficiently advanced civilization that understands chemistry and molecular biology could interpret the diagrams as descriptions of a specific type of carbon-based life with specific molecular machinery. The images of human anatomy are not necessarily interpretable as drawings of real beings, but they are potentially interpretable as schematic diagrams of a biological system. Photographs of human activities are communicable only if the finder has the ability to interpret two-dimensional images as representations of three-dimensional reality and to decode the specific conventions of photography. These are not universal. They are learned conventions that are so deeply ingrained in human visual processing that they feel universal, but they are not. Music is communicable only if the finder's processing system responds to the specific patterns of frequency and timing that constitute human music. This is the most culturally specific content on the record, and the least likely to be interpretable by a being whose sensory systems are different from human auditory systems. The Voyager Golden Record is, in the most honest assessment, a document that conveys a large amount of information to any civilization sufficiently similar to Earth's life to share the basic conventions of representation and perception, and a much smaller amount of information to any civilization that is radically different in its sensory and cognitive architecture. This is probably fine. The civilizations most likely to receive the record and make sense of it are the ones that share enough with us to have developed comparable physics and mathematics and science. The civilizations that share those things are the ones most likely to have also independently converged on some of the other conventions the record uses. What the record cannot convey to any hypothetical finder is the specific felt experience of being human, the specific quality of consciousness that experiences rain as rain, music as music, a heartbeat as both a sound and an intimate biological fact. The phenomenological texture of human experience is not encodable in any medium that can be decoded by a system that does not have that experience. Carl Sagan knew this. He knew the record was not a complete description of humanity. He knew it was a gesture, an announcement, a sample selected with care to represent humanity, as well as a 12-inch disc could represent it. He sent it anyway, because the gesture was worth making regardless of whether it would ever be received and regardless of whether a receiver could ever fully understand it. This is an interesting stance on communication. Communication is worth attempting, even in the absence of any assurance that it will succeed or that full understanding is possible. The attempt is itself meaningful. The expression of the desire to be understood is itself a form of communication. Voyager 1 carries that stance across the interstellar medium. The golden record is the physical expression of the stance. The record has been travelling for 47 years. It will travel for billions more. Whether it is ever found is genuinely unknown. Whether the attempt was worth making is not. The golden record that Voyager 1 carries is also something left behind. Not left behind in the sense of abandoned, left behind in the sense of sent ahead, a message deposited in the interstellar medium on behalf of a civilization that may not exist in any recognizable form by the time it is ever found. The record contains 116 images, greetings in 55 languages, sounds of Earth, including a heartbeat and a rain, and surf and whale song and music including Bach and Beethoven, and Blind Willie Johnson, and Chuck Berry, and a diagram of the hydrogen spin-flip transition that provides a basic unit of time and length for any sufficiently advanced civilization that finds it. The diagram is the key. The hydrogen atom's hyperfine transition, the flip of the proton's spin relative to the electrons, produces a specific wavelength of radiation, 21 centimeters. This transition is the same throughout the universe. Physics does not vary from one location to another. Any civilization advanced enough to travel through interstellar space, or advanced enough to develop radio astronomy, will have encountered this transition and will know its frequency and wavelength. The diagram uses it as a Rosetta Stone, a physical constant that both the makers and any potential finders know. The 55 languages of the greetings span the major language families of Earth's human population in 1977. Most are linguistically related to each other, descendants of common ancestral languages through the Indo-European, Sino-Tibetan, Afro-Asiatic, and other language families. A finder who decoded the greetings would hear an enormous diversity of sounds, but might, with sufficient analysis, identify the family relationships between them and the common structural features of human language. The music is the most emotionally compelling content and the hardest to decode for any civilization that lacks the specific biological substrate for producing and receiving it. Music depends on the pattern recognition capabilities of the auditory system, on the specific emotional resonances between sound patterns and psychological states, on cultural learning that teaches a listener what to feel in response to specific harmonic and rhythmic structures. A civilization with completely different sensory architecture might decode the musical recordings without experiencing anything recognizable as music. But they would know that the recordings were intentional, that something organized them, that the organization reflected the emotional and aesthetic priorities of the makers in ways that could, with sufficient patience, be analyzed and interpreted. The record itself, the physical gold-plated copper disc in its aluminum jacket with the stylus, is a kind of physical argument. It says, whatever made this had aesthetic sensibilities, whatever made this cared about what music to include, whatever made this thought that a potential finder would care about hearing rain and wind and the sound of a human heartbeat. Carl Sagan said the record was a bottle thrown into the cosmic ocean. The ocean is incomprehensibly large, and the probability that the bottle is ever found is extraordinarily small. But the throwing of the bottle was itself an act of faith, not in a supernatural sense, but in the scientific sense. Faith that the universe contains intelligence capable of receiving such a message, that the cosmos is not empty of minds other than our own, that the effort of communication is worthwhile even in the absence of any guarantee that communication will succeed. This faith is itself part of what Voyager 1 left behind, not the record per se, which is moving away from us at 17 kilometers per second and cannot be retrieved. The act of creating the record. The specific decision, by a committee chaired by Carl Sagan and involving dozens of scientists and cultural figures, to spend significant resources assembling the most representative possible sample of human culture, and place it on a spacecraft headed for interstellar space. That decision says something about who we were in 1977. It says that we were a species that had reached the threshold of interstellar communication, that understood we had reached it, and that chose to announce our existence to the cosmos, even knowing that the announcement might never be received. It says that curiosity and hope were strong enough to motivate an act that had essentially no practical payoff, and that would not be confirmed or denied within any individual human lifetime. Whether anything ever finds the record, the act of making it and sending it is permanently deposited in the human record. We know that we did it. We have the documentation. We have the record of the committee's deliberations, the debates about what to include and what to exclude. We have Carl Sagan's reflections on the process and its meaning. The record travelling through interstellar space on Voyager 1 is a physical object that carries information about us. The documentation of the record's creation is a cultural object that carries information about who we were when we sent it. both will outlast everyone alive today. That is a specific kind of left behind, and it is one of the most important things Voyager 1 will ever carry. There is a specific question that this script has been circling without naming directly, and it is worth naming before the close. The question is, what does it mean that Voyager 1 still exists? Not exists in the technical sense, still transmitting data, still functional. Exists in the philosophical sense. Continues to be a real object in the universe, a physical presence in interstellar space, carrying the record of its makers and moving away from them at 17 kilometers per second. Every other artifact of the civilization that existed in 1977, every building and machine and document and institutional structure, is either physically modified from its 1977 state or no longer exists. Buildings have been renovated or demolished. Machines have been upgraded or scrapped. Documents have been transcribed into new media. Institutions have changed their missions, their names, their personnel, their goals. Voyager 1 has not been modified since 1977, except by the natural processes of entropy and the deliberate shutdowns of non-essential systems to conserve power. It is essentially the spacecraft it was when it left Earth. The gold plating on the record has experienced 47 years of very low-level cosmic ray bombardment. The physical structure of the spacecraft has experienced the thermal cycles of the outer solar system and the cold of the interstellar medium. The components have aged and some have failed, but the object is recognizably the object that was launched, in a way that nothing else from 1977 can claim. This gives Voyager 1 a specific status as an artifact. It is not a reconstructed original. It is not a careful preservation in controlled conditions. It is an original, operating in exactly the conditions it was designed for, in exactly the state that 47 years of use in the most extreme environment in human exploration has produced. The only comparable artifacts, in terms of age and continuous function without modification, are things like ancient mechanical clocks and ancient astronomical instruments, some of which have been in continuous operation for centuries. But even those objects have been maintained and repaired by human hands. Voyager 1 has not been touched by human hands since 1977. It exists alone, in the interstellar medium, doing its work. The analogy that feels most right, though no analogy is perfect, is a letter written by someone who died a long time ago, that has not yet been delivered, that is still in transit, that will arrive at an unknown address at an unknown time. The letter was written in 1977. The writer has been dead for decades. The letter is still travelling. When it arrives, if it ever does, it will be the most ancient human message ever received, and the receiver will not know the writer, will never have known the writer. Will read the letter from the evidence of the writer's existence, the physical composition of the spacecraft, the diagrams on the cover, the sounds encoded in the grooves of the golden disk, the signals that arrive at the speed of light across interstellar distances. And from that evidence they will know that something was here, something curious, something that looked at the stars and wondered and built a machine and sent it to the dark with a letter. That is what Voyager 1 has left behind. Everything in this mission briefing is an elaboration of that simple fact. Something was here, and it wanted to be known. Here is the inventory of what Voyager 1 has left behind, stated plainly and in full. It left behind the first direct confirmation of active volcanism on another world. Eo's erupting volcanoes, observed by Voyager 1's cameras in March 1979, were the deposit that opened tidal heating as a category of astrophysical process and expanded the concept of the habitable zone to include subsurface environments maintained by tidal energy. Every subsequent discussion of Europa's ocean, Enceladus's geysers, the potential habitability of moons around distant exoplanets, traces its origin to Linda Morabito's noticing a crescent plume above the limb of Io while doing navigation work in the hours after Jupiter's closest approach. It left behind the discovery of Jupiter's rings. The rings were unknown before Voyager 1. They were faint, dark and difficult to detect from Earth. Voyager 1's cameras confirmed their existence in 1979. Together with Voyager 2's subsequent confirmation at Saturn, this discovery established that ring systems were not a peculiarity of Saturn, but a common feature of giant planets, a fact later confirmed at Uranus and Neptune. It left behind the atmospheric characterization of Titan. The opacity of Titan's atmosphere in visible light was frustrating to the science team but scientifically important. The radio occultation data revealing the temperature and pressure profile was foundational to everything that followed in Titan science. The Cassini-Huygens mission, which spent years at Saturn and sent Huygens down through Titan's atmosphere in 2005, was built on the foundation that Voyager 1 established. It left behind the pale blue dot. Not just the image, which is the most reproduced astrophotograph in history, but the perspective it embodied and the essay Carl Sagan wrote to articulate that perspective. The felt reality of Earth's smallness and isolation that the image produced in millions of viewers. It left behind the first direct measurements of the heliosheath, the region between the termination shock and the heliopause, which Voyager 1 crossed between approximately 2004 and 2012, had never been directly sampled. The data returned from it was the first observational characterization of this specific region of space. It left behind the first direct measurements of the interstellar medium in the immediate vicinity of the solar system. The local interstellar medium that Voyager 1 is currently sampling is the specific environment that the solar system has been moving through for the past 100,000 years, and the data from its measurement is the first direct evidence of what that environment actually is. It left behind a series of engineering and navigation techniques, the gravity assist maneuver as a practical mission architecture, the deep space communications protocols that allow a 22-watt transmitter to be heard across 24 billion kilometers, the radiation-hardened electronics designs that have kept a 1977-era spacecraft functional for 47 years in an environment that includes the radiation belts of Jupiter and the cosmic ray flux of interstellar space. These techniques were not invented by Voyager, but they were proven and refined by Voyager in a way that made all subsequent deep space missions more feasible. It left behind the people who built it, not literally. The people who built Voyager 1 are in most cases no longer alive, but they left behind the mission itself, which has outlasted many of them, and the science, which will outlast all of them. They left behind careers spent on a project that is still running. They left behind the culture of engineering excellence and scientific curiosity that the Voyager program embodied and that has influenced every generation of planetary scientists and spacecraft engineers that followed. It left behind a record of what human beings choose to do when they're given the resources and the opportunity to explore. The Voyager program was a choice. It was chosen over other things that the same resources could have been spent on. The specific character of that choice, the decision to build the best possible scientific instruments and aim them at planets that had only been observed from telescopes, reflects something about what science is and what it is for. The direct observation of the actual universe as opposed to the theoretical models of the universe that you can build without leaving home. And Voyager 1 left behind the question that it cannot answer. The question is not scientific. It is the question that Carl Sagan asked with the pale blue dot, that the Golden Record asks with its greetings and music, that the entire mission asks by virtue of being sent. Is there anyone out there to receive what we are sending? Voyager 1 cannot answer this. It does not carry instruments designed to detect other intelligence. It is not aimed at any planet believed to harbour life. It is moving through the interstellar medium in the direction of Ophiuchus, not toward any specific destination, following the trajectory that physics assigned it 47 years ago. But by existing, by being in interstellar space, by carrying the Golden Record and crossing the heliopause and sending back data about the space between the stars, Voyager 1 is part of the question. It is humanity's presence in interstellar space, the tiniest, most distant, most improbable presence. A spacecraft weighing 722 kilograms, powered by roughly 250 watts, transmitting at 22 watts, crossing an interstellar medium that extends for light years in every direction. But present. And the question of whether anything else is present, whether the interstellar medium Voyager 1 is crossing contains any other intelligences equivalent of Voyager 1, is the question that everything Voyager 1 has left behind is in some sense addressed to. The specific details of how Voyager 1's encounter with Jupiter was planned and what was actually observed reveal the specific nature of what First Look Science deposits. The Voyager science team had built a detailed model of Jupiter before the encounter. They had decades of ground-based observations, some spectroscopic data from passing spacecraft, and the Pioneer probe results from 1973 and 1974. The Pioneer images had been a significant improvement over ground-based observations. They showed Jupiter's cloud bands in detail. They confirmed the existence of the Great Red Spot as a coherent feature. They measured the radiation environment and established that it was intense but survivable by a well-shielded spacecraft. What the Pioneer images had not shown, in any compelling way, was the detail of Jupiter's atmospheric structure, the dynamics of individual cloud features, the character of the Galilean moons. Pioneer's imaging system was a photopolarimeter that built up an image line by line, producing the equivalent of a very slow-scan television image. The images were scientifically useful but aesthetically crude compared to what a proper television camera could produce. Voyager 1 had a proper television camera system. 2 of them, actually, both with Vidcon detectors. They could produce detailed high-resolution images of Jupiter's cloud features at a rate, and with a quality that Pioneer could not match. When Voyager 1's cameras turned toward Jupiter in the weeks before closest approach and the images began to be transmitted, the science team saw things that were not in their model. The cloud structure was more complex, more varied, more dynamically active than anything in the prior observations had suggested. Individual cloud features, ovals and eddies and jet streams, showed evidence of changing on timescales of days to weeks. The Great Red Spot was surrounded by complex interacting structures that were not visible from Earth. The boundary between the different atmospheric bands was sharper and more structured than ground-based observations had implied. This is the character of the first-look deposit, not the correction of a specific wrong prediction. The revelation that the prior model was right about some things and radically wrong about how much it had missed. Jupiter was more Jupiter than anyone had modelled it being. More complex, more varied, more dynamically interesting. The specific mechanism by which Jupiter's atmosphere produces its banding and its oval features and its long-lived structures has been studied intensively since 1979, and the understanding has improved significantly. But the phenomenon that required explanation, the specific combination of zonal jets and embedded vortices, and the specific dynamics that maintain both, was revealed by Voyager 1 in a way that gave theorists the observational grounding they needed to build better models. The Great Red Spot itself, when Voyager 1 flew by, revealed that it was not simply a persistent weather feature rotating in one direction. It was interacting with neighbouring structures, shedding material from its periphery, drawing material in at other points, embedded in a complex of smaller oval features that were themselves being sheared and distorted by the jets on either side. The red spot was a coherent structure in a highly disordered environment, surviving through mechanisms that the prior models had not fully accounted for. What Voyager 1 left behind at Jupiter was the full complexity of the planet. Not a corrected model, but the evidence that the prior model had been building a skeleton, and Jupiter was a fully fleshed organism. The Juno mission, in Jupiter orbit since 2016, has continued to extend this understanding. Juno's microwave radiometer can sense below the visible cloud tops to map the three-dimensional distribution of ammonia and water in the atmosphere. Its gravitational science experiment has measured the gravitational harmonics of Jupiter with extraordinary precision, constraining models of the planet's interior structure. Its ultraviolet imaging spectrograph has mapped Jupiter's auroras. Juno has added substantially to what Voyager 1 left behind. But Juno was built on the foundation Voyager 1 laid. The questions Juno was designed to answer were sharpened by the Voyager observations into specific scientific hypotheses that specific instruments could test. This science compounds across missions. Voyager 1's deposit is not diminished by Juno, it is amplified. The crossing of the heliopause in 2012 was not the end of Voyager 1's science, it was the beginning of a new phase. The interstellar medium that Voyager 1 entered in August 2012 had never been directly sampled by any instrument. Earth-based observations of the local interstellar medium, using radio telescopes and ultraviolet spectrographs and absorption spectroscopy against background stars, had given indirect measurements of the density and composition and velocity of the local interstellar gas. The local interstellar cloud, the specific cloudlet of warm, partially ionized hydrogen that the solar system has been moving through for the past 100,000 years, had been characterized in its broad properties, but direct sampling, putting a probe in the medium and measuring what the probe encounters, had never been done. Voyager 1 was doing it for the first time. The instruments that remained operational in the interstellar medium were the magnetic field instrument, the cosmic ray subsystem, the low-energy charged particle instrument, and the plasma wave system. The plasma wave system measures oscillations in the surrounding plasma, which it can use to infer the plasma density without directly sampling it, partially compensating for the fact that the plasma science instrument had failed in 1980. The measurements from the interstellar medium revealed that the plasma density was higher than models had predicted. The temperature was also higher than predicted. The magnetic field direction was not quite aligned with what the prior indirect measurements had suggested. Each of these discrepancies is a scientific deposit, a correction to the prior model of the local interstellar medium that will shape the next generation of models. There is a specific and interesting measurement that Voyager 1 made in the interstellar medium that is worth describing. In 2012, 2013, and 2017, Voyager 1 detected oscillations in the surrounding plasma at the characteristic frequency for electrons in a plasma of the density it was passing through. These oscillations, detected by the plasma wave instrument, allowed the team to directly calculate the plasma density from the frequency of the oscillation. This is not a trivial measurement. The plasma wave technique for measuring density requires that the plasma emit measurable oscillations, which typically requires some form of perturbation. The perturbations that drove the oscillations Voyager 1 detected were large-scale disturbances in the solar wind that propagated outward and eventually reached the spacecraft's position in the interstellar medium. By measuring the oscillation frequency at the time of each disturbance's arrival and comparing the densities measured at different times, the team built up a picture of how the plasma density varies in the nearby interstellar medium. The result was a plasma density roughly 20 times higher in the immediate interstellar medium just outside the heliopause than in the inner heliosheath. The transition at the heliopause was sharp. The medium inside the heliosphere and the medium outside it are dramatically different in their density properties, which is consistent with the basic picture of the heliosphere as a bubble of relatively low-density solar wind carving out space in the denser interstellar medium. In 2023 and 2024, Voyager 1 experienced significant technical difficulties. The flight data system, the computer that processes science data before transmission, began producing corrupted outputs that made the data uninterpretable. The mission team at JPL spent months diagnosing the problem from 24 billion kilometers away, sending commands that took over 22 hours to arrive and waiting over 22 hours for the responses. They eventually identified a corrupted chip in the flight data system and developed a workaround that rerouted data through different parts of the computer memory to avoid the corrupted chip. The workaround succeeded. Voyager 1 resumed transmitting usable data in April 2024. This episode illustrates the specific character of the extended Voyager, one mission in its late phase. It is not the science of a well-functioning instrument at its design lifetime. It is the science extracted from a 47-year-old spacecraft with failing systems, maintained by a team of engineers and scientists who were not born when the spacecraft launched, using diagnostic techniques developed specifically for this situation, across communication delays measured in 45-hour round trips. The science still comes back, imperfect, harder to obtain, requiring more effort and more ingenuity than the science of the first decade, but real, still unique, still telling us things we cannot learn any other way. This is part of what Voyager 1 left behind, the demonstration that 47 years of spacecraft operation in the most extreme environment in human exploration is possible, that a machine built in the 1970s can still function in the interstellar medium in the 2020s, that the engineering work done by teams of young people who are now old or dead was done well enough to last this long. The deposit is not just data, it is proof. The people who will receive the last signal from Voyager 1 have not yet been born in most cases. The expected timing of the final signal, the 2030s, is within the professional lifetimes of people who are currently in school or recently graduated. The team at JPL that will manage the mission through its final years is the same team that is managing it now, augmented by new hires who are learning the mission from the people who have been working on it for decades. This is a specific and unusual institutional situation. Most large engineering projects have a defined endpoint. The spacecraft lands, or the bridge opens, or the building is occupied and the team that built it disperses. Voyager 1 has had a continuous operations team for 47 years. The team has turned over completely multiple times. The mission has been supported through 7 US presidential administrations, through the Cold War's end, through the Internet's rise, through every major technological and political transformation of the late 20th and early 21st centuries. The institutional continuity of the Voyager mission is itself a kind of deposit. not in the scientific data archive, but in the organizational practices and the engineering culture that maintaining a 47-year mission requires. How do you transmit the technical knowledge needed to operate a 1970s spacecraft to a team that did not design it? How do you maintain the institutional memory of a mission that is older than the careers of most of its current operators? How do you keep a project funded and staffed through decades of changing political and budgetary environments? The Voyager team has answers to these questions, developed through 4 decades of practice. Those answers are not written down in any single document. They are embodied in the practices of the team, in the mentoring relationships between experienced and new operators, in the specific culture of a group that understands itself as the stewards of a historic mission that has lasted longer than anyone expected and will end on a timeline that is finally visible. The knowledge will not all survive. Some of it will be lost when the last Voyager 1 operations engineers retire or die. The specific operational knowledge, the tricks and workarounds and institutional memory of specific anomalies and how they were resolved will be partially documented and partially lost. This is the normal fate of institutional knowledge. It does not survive perfectly in documentation. What will survive is the data. Everything Voyager 1 has measured, the full record of 47 years of observations across the outer solar system and through the helio sheath and into the interstellar medium, is archived. The calibration information needed to interpret the data is archived. The mission documentation is archived. The science papers building on the data are in the permanent scientific literature. The data will outlast the mission. The mission will outlast the people who built it. The people who built it have already outlasted the civilization that surrounded them when they built it. This is the archaeology of a mission that is still running. The layers of context through which its meaning is transmitted, each layer adding something and losing something, the specific combination of what survives and what is lost, determining what future scientists will be able to extract from what Voyager 1 left behind. The Voyager 1 data archive is a record that will be consulted for centuries. The calibration challenges of using data from instruments designed in the 1970s, operated under conditions that were not fully understood at design time, will be a research challenge for as long as there are scientists interested in the early period of in situ interstellar medium exploration. The specific measurements Voyager 1 made, imperfect and limited and hard to obtain, are the only measurements of their kind, and will remain so until another spacecraft eventually crosses the heliopause from a different direction. That spacecraft does not currently exist. The New Horizons mission, which passed Pluto in 2015, is on a trajectory that will eventually take it to the outer heliosphere. But its instruments were not designed for heliospheric science, and it does not carry the equivalent of Voyager 1's plasma wave system. It will eventually cross the termination shock and perhaps the heliopause, but the comparison with Voyager 1 will be limited by the different instruments and different trajectory. Voyager 1 remains unique. After 47 years, after crossing the heliopause, after entering interstellar space, it remains the only spacecraft that has directly sampled the local interstellar medium with instruments designed to characterize it. There is no substitute. There is no plan to send a substitute. What Voyager 1 has measured and will continue to measure until its power fails is, for the foreseeable future, all we will have. The deposit is irreplaceable, and it is still being made. There is a specific aspect of Voyager 1's trajectory that distinguishes it from Voyager 2's, and that shaped everything that came after Saturn in ways that are easy to overlook. Voyager 2 followed the Grand Tour trajectory, using gravity assists at Jupiter, Saturn, Uranus, and Neptune in sequence. After Neptune, its trajectory carried it southward below the ecliptic plane. It crossed the heliopause in November 2018, about 6 years after Voyager 1. Voyager 1's trajectory was specifically shaped by the Titan encounter. The decision to aim Voyager 1 at Titan for a close flyby required a trajectory that, after Saturn, carried Voyager 1 upward out of the ecliptic plane rather than continuing to Uranus and Neptune. This was understood at the time and was accepted as the cost of the Titan science. The Grand Tour would be accomplished by Voyager 2. Voyager 1 would get Titan and would then depart the planetary system on a trajectory that would eventually make it the first spacecraft to cross the heliopause. The consequence is that Voyager 1 and Voyager 2 are in different parts of the sky, moving in different directions. Voyager 1 is moving roughly in the direction of the constellation Ophiuchus. In the general direction, the solar system is moving through the galaxy. Voyager 2 is moving toward the constellation Telescopium, in the opposite general direction. This matters for the heliospheric and interstellar science. The heliopause is not a perfect sphere, and the conditions in the heliosheath and in the local interstellar medium are different in different directions. Having two spacecraft in approximately opposite directions gives us two sampling points in this asymmetric environment. The comparison between Voyager 1's upstream crossing and Voyager 2's flank crossing is scientifically richer than a single crossing would have been. This was not fully planned in 1977. The full scientific value of having two spacecraft in different parts of the heliosphere was understood and was part of the Voyager mission design. But the specific value of having one spacecraft in the upstream direction and another in the flank direction for characterizing the asymmetry of the heliosphere's interaction with the local interstellar medium was not fully appreciated until both spacecraft had crossed the heliopause and the comparison became possible. The way the mission turned out was better than what was specifically planned, because the universe cooperated in ways that augmented the planned science with additional opportunities. This is also typical of well-designed exploration missions. The science from Voyager 1 and Voyager 2 is more than the science of either alone, and it is more than the sum of the two separately, because the comparison between them is itself a scientific result. The trajectory decisions made in the 1970s, based on the science priorities of that era, produced a mission that was scientifically optimal for a different set of reasons than the ones originally cited. The Titan encounter, which was the scientific justification for Voyager 1's specific trajectory, turned out to be extraordinarily valuable for exactly the reasons anticipated. But the trajectory that Titan required also turned out to be valuable for reasons that were not fully appreciated at the time, because it placed Voyager 1 in the upstream heliospheric direction and gave the pair of spacecraft a unique comparative geometry. Good science is often like this. The decision that is made for one reason turns out to be right for additional reasons that weren't fully understood at the time of the decision. The Titan trajectory decision was an example. The decision to include the plasma wave instrument on Voyager 1, which eventually became the most important instrument for confirming the heliopause crossing, despite the failure of the plasma science instrument, was an example. The decision to keep the spacecraft powered after the planetary encounters were complete, even with no specific extended mission planned, was an example. These decisions were made by people who did not know how long the mission would last or what it would eventually accomplish. They made the best decisions they could with the information available, and the decisions turned out to be better than the information available would have predicted. That is also part of what Voyager 1 left behind, evidence of good decision-making under uncertainty. Evidence that it is possible to design a mission, make decisions in the 1970s, and have those decisions turn out to be correct or even optimal, 40 years later, in a context that could not have been fully anticipated. The lesson is not that we should expect everything to work out this well. Most missions designed for a specific purpose accomplish that purpose and not much more. Voyager 1 is exceptional in how much more it accomplished than its original purpose, but the lesson is that exceptional outcomes are sometimes possible, and they tend to result from the combination of good design, conservative engineering, flexible operations, and the specific kind of curiosity that notices unexpected things and pursues them rather than filing them away as anomalies. Voyager 1 has been doing exactly this for 47 years. It will continue until the power fails, and everything it has done is permanently deposited in the human record. The specific 2023 and 2024 anomaly with Voyager 1's flight data system is worth describing in more detail, because it illustrates something specific about the relationship between a spacecraft and the civilization maintaining it. In November 2023, Voyager 1's telemetry began returning garbled data. The spacecraft was communicating and responding to commands, which meant the communication systems were functional, but the science and engineering data being returned was not usable. For several months, the mission team at JPL received signals from Voyager 1 that confirmed the spacecraft was alive, but that told them nothing about its actual condition. The team sent diagnostic commands and waited 45 hours for the responses. They analyzed the patterns in the corrupted data, looking for any information content that might help them understand what had gone wrong. They consulted the full documentation of the flight data system, the computer that processes data before transmission, going back to the original design documents from the 1970s. Eventually, in April 2024, they identified the cause. A single memory chip in the flight data system had become corrupted. The chip was part of the section of memory that stored the computer's software, and the corrupted portion was responsible for packaging the data for transmission. The computer was running normally in every other respect. It was receiving instrument data, and it was communicating with Earth. But the section of software that took that data and formatted it for transmission was producing garbage. The fix was ingenious. The team could not repair the chip. They could not replace any component on a spacecraft 24 billion kilometers away. But they could rewrite the software to avoid using the corrupted section of memory, distributing the affected code into different parts of the computer's memory so that no single corrupted chip would break the data packaging process. They wrote the code on Earth. They tested it on Earth, on simulators that modeled the flight data system's architecture. Then they sent it to the spacecraft. The command took 22.5 hours to arrive. They waited 22.5 hours for the response. The response confirmed the code had been received and executed. More waiting. Then, on April 20th, 2024, Voyager 1 began returning readable engineering telemetry for the first time in 5 months. More updates to the code, restoring science data, took additional months. The team described the experience as the most challenging in the mission's history, which is a remarkable statement for a mission that has been operating for 47 years. What it required was knowledge that existed nowhere but in the minds of the people working on the problem and in the original design documents from 50 years ago. The flight data system architecture is not something that anyone in the current generation of spacecraft engineers designs with. It is a relic. Its documentation is complete but written in the technical language of a specific era and requires expertise to interpret correctly. The team members who understood the flight data system well enough to devise the fix were in their 50s, 60s and 70s, people who had spent their careers on Voyager, who had built up the specific knowledge of this specific system over decades. Their knowledge was not easily replaceable. Their ability to solve this problem was the product of a lifetime of work on a mission that most planetary scientists consider closed. This is the hidden vulnerability of the extended Voyager 1 mission. Not the failing hardware, which was anticipated, the aging expertise. As the engineers and scientists who understand the spacecraft systems in depth retire or die, the ability to diagnose and fix anomalies decreases. Some of that knowledge is documented. Some of it lives only in the heads of the people who have been doing this work for decades. The 2023 to 2024 anomaly was solved because the right people were still available to solve it. A similar anomaly 10 or 15 years from now would be solved by people who are learning the system from documentation rather than from a lifetime of direct experience. It might still be solved, but it would be harder. This is also part of what Voyager 1 is leaving behind. The institutional knowledge of how to operate a deep space spacecraft across timescales of decades, accumulated by a team that will not be around indefinitely. The documentation is being written, the oral history is being captured, but some of it will be lost. That is the nature of expertise. It is partly transferable and partly not. The part that is not transferable is the most valuable and the hardest to save. Voyager 1's final years are as much a race against the loss of expertise as they are a race against the loss of power. Both will run out eventually. Will run out. The question is which first, and what is preserved in the interval. There is one more category of what Voyager 1 left behind that has not yet been addressed, and it is the most diffuse and perhaps the most important. It left behind a way of thinking. The Voyager missions were among the first planetary exploration programs to be designed with full awareness that they were part of a tradition of scientific exploration that extended backward in time and forward into the future. The people who designed the missions thought about what previous missions had left them to build on, and what they were leaving for the missions that would follow. The design decisions, the choice of instruments, the trajectory choices, the decision to include the golden record, reflected an awareness that the mission was a link in a chain, not a standalone event. This awareness is a specific intellectual stance that was not universal in the history of science and exploration. Much of the history of exploration was driven by immediate objectives: find gold, claim territory, be first, demonstrate technical achievement. The Voyager program was oriented towards something different. Understand the solar system as a complete system, leave the best possible dataset for future scientists, build on what was known and extend it as far as the technology allowed. The specific way that Voyager 1 deposited science is a model of this stance. Every instrument was designed to produce calibrated archival data. the calibration protocols, the data format, the documentation of the observation sequences, were all done with an awareness that the data would be used by scientists who had not been involved in its collection, potentially decades later. This orientation is now standard in planetary science. Every major mission produces data archives that are publicly available and designed to be used by the broader scientific community, not just the instrument teams that built the instruments. The Planetary Data System, the NASA archive that stores and distributes planetary mission data, was built partly on the lessons learned from the Voyager program about how to make scientific data accessible and usable across time. The idea that scientific data belongs to the scientific community and not just to the people who collected it, and the specific practices that make this idea operational, were developed and refined by the Voyager program and others of its era. Voyager 1 left behind an archival tradition. The archival tradition is different from any specific scientific result. It is a set of practices and norms and institutional structures. It is invisible in the same way that the grammar of a language is invisible. You use it without noticing it, and you only notice it when it is absent or defective. Planetary scientists today who analyze Voyager data to extract new science from it, using analytical techniques that were not available in 1977, and addressing scientific questions that were not yet formulated in 1977, are using the archival tradition that Voyager 1 helped establish. They are benefiting from decisions made 47 years ago about how to record and calibrate and document and store data. This is the most direct form in which Voyager 1 left behind a way of thinking. The specific scientists who built the Voyager instruments are mostly gone. The culture they embodied, the specific combination of scientific rigor and archival discipline and long-term thinking that characterized the Voyager program at its best, is partially transmitted and partially lost. But the practices it produced, the actual protocols and standards and formats that make the data usable today, are still operational. Voyager 1 also left behind a specific kind of relationship between the public and space exploration. The Voyager planetary encounters, particularly the Jupiter and Saturn encounters in 1979 and 1980, were public events in a way that few subsequent planetary missions have matched. The images were released to the public as soon as they were processed. The press conferences at JPL were watched by millions of people. The scientists communicating the discoveries were not bureaucratic spokespersons, but the researchers who had actually made the discoveries, able to speak with genuine enthusiasm about what they were seeing. Carl Sagan was the most visible of these, but he was not unique. The Voyager science team had multiple members who were excellent communicators and who understood that their role included explaining the mission's significance to a public whose tax dollars had funded it. The relationship between the scientists and the public during the Voyager years was more direct and more participatory than it has been in many subsequent missions. This relationship has been partially reconstructed by social media and streaming video, which allow people to watch spacecraft events live and to interact directly with mission scientists. But the specific character of the 1979 to 1981 period, when the discovery of Jupiter's rings and Io's volcanism and Titan's opacity were being made in real time by scientists communicating their astonishment directly to a public that was watching, is not fully reproducible. Voyager 1 left behind that relationship as a precedent, as a model of what public engagement with science looks like when it is done well, as evidence that the public cares about exploration, finds genuine beauty in planetary images, and is capable of appreciating the significance of discoveries that require some background to understand. The public engagement with Voyager 1 in 1977 to 1981 was the foundation on which subsequent public engagement with planetary exploration was built. The Mars Curiosity rover's landing in 2012 was watched live by hundreds of millions of people, partly because the precedent for watching planetary events live had been set by Voyager. Voyager 1 left behind the expectation that space exploration is something that happens in public, for everyone, with the discoveries shared as they are made. That expectation is now so deeply embedded in NASA's culture, and in the public's expectation of NASA, that it is easy to forget it was established rather than assumed. It was established, and Voyager 1 was one of the primary instruments of its establishment. The last thing Voyager 1 will leave behind is the record of having been the first spacecraft to visit Jupiter in detail, the first to see Io's volcanoes, the first to confirm Jupiter's rings, the first to photograph Titan's haze from close range, the first to cross the heliopause, the first to enter interstellar space. These firsts are permanent, no spacecraft can be the second first. Whatever else is learned about Jupiter, whatever other spacecraft visit the heliosphere, whatever future technology eventually sends something deeper into the interstellar medium, Voyager 1 was first. The weight of being first is a specific kind of deposit. It creates a marker in time. Before Voyager 1, these things had not been done. After Voyager 1, they had. The moment is permanent. The record is irrevocable. Voyager 1 will be in interstellar space long after every human institution and every human language and every human memory has been transformed beyond recognition. Its physical presence in the universe, carrying the records of what it found and who built it, is the most durable form of the deposit it has made. Everything else this script has described, the science, the images, the archival tradition, the public engagement, the culture, the perspective, is less durable. It is maintained in human institutions and human memories and human archives, and human institutions and memories and archives are temporary by the standards of the universe. But Voyager 1 itself is out there, and it will be out there for a very long time, and the fact that it is out there, and that it got there from here, from this planet, from this civilization, by the effort of specific people who were born and died and left their work behind, is the deposit that cannot be lost as long as the universe continues. We were here, we looked out, we sent something. That is everything Voyager 1 has left behind, and it is more than enough. There is one more specific deposit that Voyager 1 left in September 1977, before it even left Earth orbit, that tends to be forgotten in discussions of the mission's scientific and cultural legacy. It left behind proof that it was possible. This sounds trivial. Of course it was possible, it happened. But the knowledge that something is possible is itself valuable in a specific way. It changes the space of what future designers and planners will attempt. Before Voyager, the outer planets had been visited only by the Pioneer probes, which were designed as relatively simple explorers without the sophisticated science instruments and high-resolution imaging systems that Voyager carried. The Grand Tour concept, using gravity assists to visit all 4 outer planets in a single mission, was known theoretically but had never been demonstrated. The navigation accuracy required, the telecommunications architecture needed to return data from Saturn and beyond, the instrument designs that could survive the radiation environment near Jupiter were all unproven at the Voyager scale. Voyager 1 proved them all. The demonstration that a spacecraft could be built, launched and operated to produce the quality of science that Voyager 1 produced at Jupiter and Saturn, that it could survive the radiation belts of Jupiter, that it could navigate with the accuracy required for the Titan encounter, that it could transmit data at Saturn's distance. All of this was new knowledge about what was possible. The missions that followed Voyager, the Galileo Jupiter orbiter and the Cassini Saturn orbiter, and the New Horizons Pluto flyby, and the Juno Jupiter orbiter, and all of the other outer solar system missions of the subsequent decades, were designed with the knowledge that Voyager 1 had established, that these things are technically possible, that spacecraft can operate reliably in the outer solar system, that the science return justifies the investment. None of that knowledge existed before Voyager 1. The demonstration missions that establish the feasibility of an entire category of exploration are not always recognized as the most important missions in a program. They are often overshadowed by the follow-up missions that build on their proof of concept to do more detailed and more targeted science. Galileo's Jupiter science was in many ways richer than Voyager 1's. Cassini's Saturn science was far more detailed. But Galileo and Cassini were possible because Voyager 1 existed. The deposit of proof of concept is a deposit made to the future. It does not show up in any individual scientific paper. It shows up in the institutional confidence that makes it possible to approve and fund the next mission. It shows up in the engineering culture that builds on demonstrated techniques rather than reproving the basics. Voyager 1 left behind that confidence, that culture, and it left behind, finally, the specific and peculiar fact that a machine from 1977 is still sending data in 2024. Not because anyone planned for this, not because the mission was designed for 47 years of operation, because it was built well, launched well, operated well, and kept in power by the slow decay of a radioactive element, and because the science that could be extracted from it justified the continued investment in keeping the antennas pointed at it and the engineers available to interpret what it sent. The fact that it still works is the most direct statement of what was left behind in September 1977. Something was built that lasted. In a civilization that builds things meant to last for years or decades, something was built that lasted 47 years and is still running. That is the final deposit. And it is the one that says the most about who we were in 1977 and what we were capable of when we worked at the frontier of what was possible. We were capable of this. We are still capable of it. The machines we build today, launched from this planet with this technology by people working with this level of care and ambition, will also be transmitting in 2071. If we choose to build them. There is a thing about Voyager 1 that gets lost in the science and the culture and the philosophy. It is a machine, not a metaphor, not a symbol, an actual machine. Aluminum frame, copper wire, titanium bolts, silicon circuits, magnetic tape, nuclear fuel pellets, a rotating antenna dish, 11 instruments that were designed and built by specific people in specific workshops and laboratories in the 1970s and tested and launched and flown. And this machine, built by people who are mostly dead, designed by computers less powerful than a modern wristwatch, launched by a rocket that has not been manufactured in over 40 years, is currently 24 billion kilometers from the place where it was built, sending back data about the interstellar medium. The machine is still there. This is the fact that everything else in this mission briefing has been circling. The civilization that built it has changed so completely that it is, in most practical senses, a different civilization. The people who built it have died. The tools used to build it are museum pieces. The institutional context, the Cold War, the specific geopolitical tensions that gave NASA the funding and the urgency to do planetary science at that scale, is gone. The machine is still there. This is what it means to build something well, not that it lasts forever. Nothing lasts forever, but that it lasts longer than the context that produced it. That it outlives the civilization that built it, and continues doing the work it was designed to do in an environment that the people who built it could imagine but could never visit. Voyager 1 is the most extreme example in human history of something built well. Not the most technically sophisticated, not the most powerful, not the largest or the most expensive, but the farthest from home, the longest lasting in the most extreme environment, the most unambiguously and demonstrably still doing its job. When the last signal arrives, whenever that is, it will not be the end of the mission in any sense that matters. The data is already archived, the science is already deposited, the image of the pale blue dot is already in circulation. The discovery of Io's volcanism is already in every planetary science textbook. The archival tradition is already embedded in how NASA stores and shares data. The public engagement precedent is already the baseline expectation. The deposits are permanent. The machine will continue in silence, following the trajectory that physics assigned it in September 1977 for as long as the solar system exists, and long after the planet that built it has been changed beyond recognition by the sun that warms it. Something from this world will still be out there, moving, carrying the record of what we were. Leaving behind everything we have made, that is Voyager 1, that is what it left behind, and that is everything. Strap in, keep looking outward, and stay with the crew. If you want more mission briefings like this, subscribe for the next journey.